No.
Nothing wrong.
Number 7.
Okay, so this talk will be about primes and arithmetic progressions, and also about Sieve theory. It's split in two. I'll give the first 30 minutes in which I talk about Dirichlet's theorem on the infinitude of primes and arithmetic progressions. This, although strictly not necessary for the goal of the talk, which is Linnik's theorem, which I will introduce shortly, it does provide a lot of important background, and so I would like to cover it briefly. Okay. So let us fix an integer q, okay. And then for a residue class A on q, we want to answer some questions about primes in this residue class. For example, are there infinitely many primes in this residue class? If so, when does the first one appear? Okay, so these are two very fundamental questions, and we happen to have decent answers for both of them. So, for example, okay, maybe more concrete, if q is equal to 10, then we may want to ask the question, are there primes that end with the digits 1, 0, 3, 9? Several of these are obviously degenerate in the sense that, for example, if A is 0, 2, 4, 6, 8, and so on, then there will not be very many primes in there. Okay. But in the other cases, okay, similarly, 5, there will not be very many primes in there. But for the other cases, we may wonder, are there infinitely many primes that end with the digit 7? And Dirichlet answers this question. He did so in 1837. Okay. Before I do that, let's tackle the case of the trivial arithmetic progression, in which it's just the integers. Okay. So step size is 1. And Euler answered this question a century earlier, 1737. So let me give you Euler's proof, which will generalize to Dirichlet's proof. Okay. So Euler started with the Riemann-Siegel function, which is defined as the sum from n equals 1 to infinity of n plus whatever n is. And it converges absolutely for the real part of s greater than 1, but for now, okay, because this is just background, I will not talk about convergence at all. He found that he could factor this as a product, as so. A product over all the primes. Why is this true? It's because when I factor this product out, then what that means is I'm choosing one element, one term in each of these factors. In other words, I'm choosing a power of p, okay, for every prime p, and when I multiply that all out, I get one unique way of factoring an integer n in terms of primes, and so I get 1 over n plus. Using geometric series, I can rewrite this as O. And this is known as the Euler product. Okay. And note, because this will be important later, this manipulation works for more general things other than just the number 1. Okay. For example, if I consider a product 1 plus f of p, over p to s plus f of p squared over f of p. And so on. Okay. I can perform the same argument. I can choose one term in each of these things and multiply it all out. The denominator will now be n to the s, and if we have that f of ab is equal to f of a times f of b for all a and b, this is known as complete multiplicativity. Complete multiplicativity. Then the same manipulation works. Okay, I expand out the product, and then it goes into both of the forms. And this is known as the Dirichlet series with coefficient f, evaluated at the complex parameter s. So if we have completely multiplicative, if f is completely multiplicative, then we get this nice factorization. And the main example is the Riemann-Siegel function. Okay. So is what Euler did to show that there are infinitely many primes. So observe that from this formula, one can take logs and get log of the s is equal to negative some s. And using the Taylor series of log, I can write this as so the error term, is just some constant. Forget about it. The main term, the main point is that by using logarithms on this product, I now get a sum that looks a lot like the original sum, but with primes instead of n. And now, famously, this sum diverges, okay? And more quantitatively, this is about log x, okay? And so I'm going to abuse notation and say that zeta of 1, which is the value of this sum, is equal to the logarithm of infinity. Again, this is just for background, okay? I'll be setting up things that I will be using later, so please do not yell at me for not being rigorous. And then this thing allows me to conclude that taking the limit as s goes to 1, okay, I get the sum of 1 over p is equal to log of infinity. Okay. And so therefore, there are infinitely many primes.
Euler literally wrote this, actually. And it took a while to actually make rigorous what he was saying.
Yes. In fact, we can make it rigorous. In fact, Merton said so. Okay, this is called Merton's second theorem, which I will be using later in the talk. All of this is planned. I can show rigorously that the following is true. Little o of some error term that you don't need to remember. So that is one rigorous way of saying this log infinity nonsense. So what does Dirichlet want to do? How do I use this to show that there are infinitely many primes in arithmetic? Oops. Infinite number of primes. So the naive thing to try is, let's do this sum. For my fixed modulus q, that's called the modulus, and a residue class A mod q, let's just consider this sum. This is pretty close to what I had above, okay? But the main tool that we used in this part was the multiplicative. But unfortunately, this function here is not multiplicative. So we cannot play the same game. But fortunately, Fourier analysis saves us. Okay, so this is our goal. We would like to understand this guy. And the main issue is that it's not multiplicative. But Fourier analysis tells us that we can decompose functions like this into multiplicative pieces. Okay, so allow me to briefly set up some notation. If we consider the group G, which is the multiplicative group Z mod QZ, okay, this is abelian, this is a standard factorized introductory algebra. Okay. We can define the Fourier transform. So there's a dual group, which is all of the group homomorphisms from which the group homomorphisms will be denoted by from Z mod QZ star to the unit circle in the complex values. Okay. We define the Fourier transform as follows. And there is also a Fourier inversion formula for the people who have seen the Fourier transform on real line. The formulas should look pretty familiar. Okay. So this is just some Fourier analysis. And choosing f of x to be the indicator of x is equal to a, okay, this formula produces, evaluating the Fourier transform using this formula, we get that 1 on xa equal to a is 1 over g So why is this good? It's because by definition, these characters are multiplicative. Okay. So right now they're just multiplicative functions on this group, but I can extend them to the integers. So what I can do is I can extend by 0 to a function z mod q(z) to the unit circle, which I'm going to call t, okay, for torus. And I can extend by periodicity to a function from z into the unit circle. Okay. So these functions, once I do this extending, will be multiplicative, in fact, completely multiplicative functions on the integers. Okay. And so I can play the above game. So using that formula, I can rewrite the sum as 1 over g pi a r, and again, interchanging summation freely, I get the following. And the important part is now this is the Dirichlet series with a multiplicative function.
Also easily, yes. If you want to PTS on the right, you want PTS on the left as well.
Yeah. So. And so this, I can now play my above game. So playing the above game, this is equal to, like, literally doing the above thing in reverse. This is equal to the sum of the logarithms plus some parameter which we can ignore, where this
S is larger than 1.
Yes. Again, we ignore convergence. Okay, just pretend it's formal. And this is the logarithm of the product of 1 minus chi p, pps, 1. And this guy is exactly analogous to what I had above. F there is my chi here. Okay. And this is called the L function associated to the Dirichlet character chi. Writing it out this way as a sum, it looks like that. So for analysis, converts this thing into multiplicative things, and then we can use the above trick. So now let me introduce the principal character, which is very important. So a very easy example of a character on this group is called the principal character. And that's the thing that just sends everybody to the number 1. That's the principal character. And let's compute ls of chi 0. Okay. Because here, I'm summing over all characters. So I will need to understand the logarithm of ls chi for all characters. I will now do the example of chi equals chi 0, which is called the principal character. Okay. By the product formula, this is the following. But chi 0 is 1 on this thing. In other words, chi 0 of p is equal to 1 for all p not dividing q. Okay, because p not dividing q will mean that p is in this group. And so this is the same thing as p not dividing q, 1 minus pi, sorry, 1 minus 1 over pps is 1. And so taking back the p dividing q bits, okay, this is just a factor times the full product, which is just the Riemann zeta function. So in other words, because the Riemann zeta function has a pole at s equals 1, right? I told you it blows up there, so will ls chi naught. So it will also have a pole at s equals 1. So it has a pole. And so, in particular, we have that logarithm of L1 chi 0. Again, please be loose about this. This is good news because here I have that this product, this sum that we're interested in, is some sort of average over characters of the logarithms of these L1 chi's. And I told you that one of them is already infinity. So we would be happy, we would win, if we managed to show that none of the others, we would win, if the logarithm of L1 chi, for chi not equal to the principal character, is not equal to minus infinity. Or in other words, L1 chi is not equal to 0. Because then, none of these terms, sorry, all but one of these terms will be not infinity, not negative infinity, and one of them will be infinity. And so this whole thing will be infinity, and this thing will be infinity, and then we will conclude that there are infinitely many primes in this arithmetic progression. Okay. So we would win if this is the case. Okay. Now this is the crux of this starting section. Okay. What might be an issue for this? Okay. So first, let me tell you a big theme. There's a major theme in analytic number theory called the dueling conspiracies. And this tells us that it is more difficult, okay, it is difficult for us to prevent one bad thing from happening. But if two bad things are happening, then we can use those to play against each other and then rule that out as a contradiction. Okay. So an explicit formulation of this, in this case, not formally, is at most 1 chi can be bad. And quantitatively, this is a simple computation reveals that the product over L as chi is bigger than 1. Okay. So at s equals 1, okay, you cannot have two of these L functions being 0, because only one of them can be infinity. Okay. That's another computation in conditional convergence of series. But this tells us that at most 1 chi with L1 chi equals 0. And this is powerful enough to rule out a lot of characters. Okay. In particular, this rules out complex characters. So if chi does not equal to chi bar, the complex conjugate, then we observe that L1 of chi bar is equal to L1 of chi bar. This is just something you can observe from this formula. And so if one is 0, then the other will be 0. And then we get two different characters who vanish. Okay. And this is not possible. And so the complex character case has been ruled out by the dueling conspiracies argument. Okay. And so what's left? What's left is if chi is real valued. In other words, chi is a map from z mod q z star to plus or minus 1. Okay. And this is called a quadratic character, because chi squared is equal to chi naught. Okay. When I square chi, then it will only be 1. Okay. But the character which only maps to 1 is the principal character. Okay. So that is why it's called quadratic. And we see that that is now the most difficult case to rule out. What could go wrong? So there are two extreme cases, extreme scenarios, and it happens that chi is in the middle. So what is one extreme? One extreme is that chi p equals plus 1 for all p. And this, as of what I've said so far, it might happen. In this case, ls chi is equal to the product of 1 minus plus 1 over p, and that's just the Riemann's latest function. Okay. In other words, as a whole, at s equals 1. And this is fairly easy to rule out. Okay. If chi is not the principal character, then it's fairly easy to rule out that it has a pole at s equals 1, because in particular chi is mean 0. If you sum over like an interval length q. And this is enough to tell us that this is the. So this is a.
Can we use more obligative to say it's chi naught? If chi is 1 on the primes, every number is the product of primes, doesn't that make every number have value 1?
Yeah. So this is chi naught. Right. And
This argument is more robust. Since I think if 99% of the primes are 1, this would also be a valid argument.
Right. Thank you. So that's the extreme, the extreme case where it correlates with 1. Okay. And this is fairly easy to rule out. So fairly easy. We will be encountering this case again in the proof of Linnik's theorem. Okay, let me give the other case and then talk about the appearance of Linnik's theorem. So the other case is if pi p equals -1 for all p. So in other words, there's a function, okay, let me define the Liouville function. This is defined to be lambda p equals -1, and extending by multiplicativity, okay, lambda of n is equal to -1 times the number of prime factors, counting multiplicity. So this is called the Liouville function. It's kind of going to show up again. And what about in this case? Then, let me give you the following computation. This is equal to the product of 1 minus 1 over p, 1 plus 1 over p, which is 1 minus 1 over p squared. And again, playing the same game, we expand out the product. We see that this is actually equal to the sum over n, where n is a square. Okay. Because all of these things, when you write it out using the geometric series, all the primes will have even exponent. Okay, and so all the things that they multiply to will be squares. Okay. And as s goes to 1, okay, as s goes to 1, we get that zeta of 1 times L1 of lambda is equal to sum over n over n squared, which has a specific value. But this means that because this guy has a pole at 1, this guy ends up having a 0. Okay, this is not a rigorous proof. Okay, proving it rigorously actually is the prime number 0. But the intuition is that if chi correlates with the Liouville function, then we do get vanishing, which is the thing we want to prevent. Okay. So it might happen that chi behaves a lot like the Liouville function, in which case L1 of chi might actually end up being 0. Okay. So we have to rule this out. Okay. I won't tell you how you do it, but I want you to keep in mind that there are these two extreme cases. Either chi is 1 a lot, or chi is -1 a lot on the primes. Okay. And this one is fairly easy to work with. Okay. In fact, Hunter will do so in his talk. This one is a little more difficult. Okay, we will unfortunately have to skip it. But the arguments that Hunter will give are kind of similar. So just keep in mind that there's this major issue about these chi's conspiring in the extreme, and it's not the spectrum. So that is all I wanted to say.
We started with Euler.
Yeah.
Right? I mean, I think it's called Euclid's proof. But
yeah. No, it's Euclid's theorem that there are infinite primes. But
so, well, I mean, primes, product of primes plus 1. Is there an analog of product of primes plus 1 for arithmetic operations?
It's there are some math overflow posts talking about this, and I think the answer is no.
Okay.
It doesn't work in all cases. It works in many cases, and there's some algebraic number theory, blah blah blah, but not in all cases.
But there's no child's proof.
Yeah. So Dirichlet, I think, is the best.
For example, 7 mod 10. If you want many examples 7 mod 10, Dirichlet's proof is still the only proof, well, and its descendants are the only proofs available. Yeah, Euclid would probably do it.
Or whoever he copied, right? I mean,
Yeah.
Right? He compiled a book.
Fine. Yes.
Thank you, Daniel. Yeah, so this was all the question of, are there finitely many primes or are there infinitely many primes in an arithmetic progression? And Linnik's theorem is asking, what's the first time I see a prime in an arithmetic progression? Right, so we might attempt to try the same proof here, but it doesn't immediately tell us how the primes are distributed among these arithmetic progressions. It just tells you there's infinite limit. We can't immediately read off when does the first one appear. But we can naively try to adapt this proof and say, I can look at sums of the form n less than x, or p less than x, of the indicator p equals a mod q over p to the x a. And so what's the first value of x for which this guy is positive, right? Instead of furnishing a proof that this guy is infinite, I might try to say this is bounded from below by 0, or by some positive quantity. Yeah, so this is what we are going to try to do with Sieve theory. Whenever we see a sum over primes, this is something that Sieve theory can handle. Let's, before looking at this, take a look at a much easier problem of saying which numbers are prime in a certain range, such as this one. And this is something that many of us might be familiar with, either from grade school or otherwise. If we listed out all the numbers from 1 to 100, all we need to do is look at 2, 3, 5, 7, cross out all of their multiples here, and then say none of those guys can be prime. Cross out a bunch of numbers, and we're left over with some guys here. And we know exactly which ones are primes. And so we might expect, maybe I can convert this qualitative idea of saying, I can do this crossing out business into a quantitative estimate of saying, maybe I can estimate the sum of root x less than p less than x of 1 over the primes between root x and x. Can I convert this argument to something quantitative? And the answer is yes, hopefully. We can write inclusion-exclusion. We can't do the same naive thing. We have to keep track of, well, if I cross out the multiples of 2 and the multiples of 3, if I subtract them off from this sum, in other words, they'll have some overlap. So what do I mean? This is exactly equal to the sum from root x over all the integers n between root x and x of just 1. And then I subtract off over the primes less than root x all of the multiples of p in this range. Right? So this will be the sum of root x less than or equal to np less than x of 1. Okay. And like I said, there will be some overlap, so I need to add back the guys that are products of at least 2 primes. Note that I have to have some kind of ordering constraint on here, otherwise I'll be over-counting. And then you can do the same thing with 3 primes, P1, P2, P3. Same idea. And so on and so forth until you run out of things. And we can say, oh, each of these sums are relatively easy to handle. For example, this sum I can estimate by, say, x minus root x, plus probably some small error. This sum I can say is probably x minus root x over p plus some small error, etc., etc. Sorry. Let's use some notation because there's a lot of overlapping things, right? I'm seeing a lot of x minus root x's, I'm seeing a lot of errors pop up. And the hope is that if I handle the errors correctly, I'll be able to get a precise, or perhaps not precise, but at least a good estimate of how many primes there are between x and root x. So, for example, with the 1 prime scenario, or let's even start with all the guys, all of the integers between root x and x. This is x minus root x, the number of integers, plus maybe some r1, where r1 is big O. And this can happen if x or root x is not an integer. And similarly, the sum where now I'm looking at the guys that are divisible by a p, so p divides n. This is equal to x minus root x. I'm only keeping 1 over p of these guys. So expect this. I'm going to index the remainder term by rp, and again, rp is big O. And I can do the same thing with any number whose prime divisors are all less than root x, right? So if I do the same, this will be x minus root x over d plus r sub d, or r sub d is, well, big O of 1. Right. So for notation, I'm going to say capital X is equal to x minus root x, and g of d is equal to 1 over d. This way, I can simplify this expression to capital X times g of d plus r sub d for any d whose prime factors are less than root x. And I should insert this back in there, and what do I get? So I got the sum of root x less than or equal to q less than x is of 1 is equal to the sum over all d whose prime factors are all strictly less than x. So this will account for all of these sums in the inclusion exclusion. So sum over d and d should be square root of exactly this quantity. So I get x times g of d plus r sub d. And I need to account for this sign change, right? Some of these are positive, some of these are negative, so I insert a mu of d. Where mu of d is plus 1 if d has an even number of prime factors, mu of d is minus 1 if it has an odd number of prime factors. For our purposes, it's essentially the same thing as a Liouville function. I don't want to get too far into it. As Daniel said, right, there's a lot of multiplicative structure that we can exploit when we see sums like this. So I can separate all the r sub d's away. And I'm left with the sum. I factor out the x. I'm getting a sum over d of mu of d, mu of d, plus some sum of r d's times mu of d, but I'll put this into a big O estimate. Okay. And I would expect this guy to be a reasonable estimate for the number of primes between x and root x. However, there's a big problem, and it's that this error term is way too big and it's out of control. Right?
Did we lose the main term?
This one here would be the main term. So I've collapsed all of these sums together.
I mean, the sum of 1.
D equals 1 is part of the first sum.
Ah.
Yeah.
Okay. I guess 1 does have all prime factors less than root.
Yes.
So this is what we want to be the main term. We want to be able to estimate this guy. However, we have this big problem of having too much error that overpowers the main term. So, I mean, the naive thing to do is to just say, well, don't do all of that, right? I can stop this process maybe over here. And in fact, it's perfectly reasonable to say that in this case, if x was 100, I do not need to consider d bigger than 100. That tells me no extra information and costs me a lot of error. Right. So I should be cutting this guy off at d less than some, say, capital D. However, that conflicts with my expression over here. Right? This will no longer be a precise inclusion-exclusion, and I'm no longer left with a hopefully precise main term. It'll be somewhat off. And the more terms I throw away to save on the error, the less accurate my main term will be. So we have to handle this trade-off somehow. So. To simplify the notation a little bit, and so I don't have to write out d has no prime factors less than root x every single time I do this. I'd say capital P of root x is equal to the product over the primes less than root x of, it's just the product of all the primes less than root x. So that d has no prime factors less than root x if and only if d is, if d divides P of root x. Right. And so in our sieve, what we end up with is we get the sum over root x less than p less than x of 1. Well, this is equal to the sum of root x less than or equal to less than x of the n that are co-prime to p of root x. Right? We've tossed away anything that has or is a multiple of any d dividing p of root x. So n is co-prime to p of root x. And we're saying that it is equal to x times the sum over d dividing p of root x. Mu of d, p of d, plus some big O of imaginary terms. So right now I can write this as a Euler product actually, and I can factor this as the primes less than root x of 1 minus p by doing the process that Daniel said. You expand it out and you collect the like terms, and using the fact that g, which was defined as 1 over d, is completely multiplicative, magically works out, and the minus signs line up with the mu of d. So this is very nice. Merton's theorems tell us a way to quantitatively estimate this guy, and we have a very good understanding of how to do that numerically. But again, like I said before, we have a trade-off, right? There's too much error here. I want to say I'm only keeping all the d less than or equal to some capital D, right? It's reasonable to say d should be equal to x or so. And so I have to do the same thing on this side. I can't keep all of these guys around. But this is additionally at the cost of saying this is no longer precise. This is kind of an approximately equal to. So this lost a lot of its multiplicative structure. This is no longer equal to an Euler product. But a bigger problem is that I've lost a relationship between the two sides. I don't even know if this is an upper bound or a lower bound or how close it is. We do expect it to be a reasonable estimate, right? The bigger d is, the more precise we expect this process to be. But yeah, in fact, the fundamental lemma of Sieve theory formalizes this. It says that if you do this tossing away business and make some smart choices along the way, this is equal to 1 plus big O of e to the minus 1b over 1 x. So it gets exponentially better the more error you can handle, but yeah, that's not.
That factoring times the product down there.
Yes, I'm sorry. So yeah, this is very good if we can tolerate a lot of error, but in practice we usually cannot. In this case, we can take d up to x, perhaps x, a power of x slightly less than 1, but we cannot hope to improve upon that. Because, like I said, if you keep d larger than x, we're using a lot of redundant information on the table, right? And it's only costing us error, it's not giving us anything in return.
If we jiggle x, don't we expect the remainders to be kind of random?
Yes, we do.
But it's very difficult to.
It is hard to predict.
The problem is that the Mobius function is still around. There's also the mu of d, and understanding mu of d is as hard as doing the rest of number theory. So yeah, it's a sum which it's historically been very hard to extract cancellation. We suspect lots of cancellation, but we don't have any tools to actually prove it.
Process for a moment.
Does anybody else have questions, please?
No. I mean, you're almost telling me we wasted our time getting to this point. The first term, you say we don't understand, and the second term, you said was bad.
No. The first term, if okay. So d here, there's a limit of how we can do. Capital D.
Yeah.
The capital D in the e to the minus log. That's sort of, there's a limit on how good we can do on that because of the error.
Yeah.
But if we instead take root x to be a smaller power of x, say x to the epsilon, right? Then we're no longer counting primes, but we're counting, things with a bounded number of prime factors.
Okay. So this story is not going to come to a conclusion. We're going to change the question.
It's actually one of the great embarrassments of Sieve theory that it cannot even recover Euclid's theorem. That pure Sieve theory alone cannot prove there's infinite many primes. Without using an input that's a lot stronger than Euclid's theorem. Yeah, no, it's actually no, that's not quite true. Yeah, actually, if you just want Euclid's theorem, but yeah, if you want to say the right number of primes, you can use x and x.
Okay.
It's very, very sad.
Yeah.
But let us return to this question of, okay, I have to cut it off at some point. Otherwise, the error becomes unmanageable. And in practice, there are hard limits to what this capital D can be before those error terms become overwhelming. So part of Sieve theory is answering, given some limit to how big capital D can be. What's the best I can do? Yes.
So remember, so there's no way of jiggling x to make the right? Putting absolute values on RD is a brave thing to do, right?
Yes.
We can't say, oh, if I jiggle x, they're plus and minus at random and it's much smaller?
No.
Okay.
We would hope so, but unfortunately, yeah, we're stuck with this. So in practice, we have this limit, right? This log d over log root s is at most 2. There's nothing better we can do. Right? And so the question becomes, well, what is the best that we can do? And so Sieve theory has produced an answer. It says if you run the inclusion-exclusion in a very clever way, you toss away some terms, you keep some terms, you might even toss away some terms smaller than capital D. But if you do this in an optimal way, you can furnish some good lower bounds and upper bounds, and we can precisely give what the best upper and lower, not the best, but some upper and lower bounds are. So there's a great black box that we will now state, and we will, I'm sorry.
Let him be.
So the black box is as follows. Right? We want to handle these terms, but I only want to keep some of the muties, and I might toss some of them away to be smart and retain, instead of just an approximately equal to, a hard upper bound or a hard lower bound on the left-hand side. Right? So the great black box says that, and I have it written down over here. So let G be a multiplicative function with 0 less than or equal to G less than 1. And we'll set the quantity V of Z to be that product over there, where Z is the limit to which primes we are running inclusion-exclusion on. So V of Z is the product over P less than Z of 1 minus P of P. And we have a slightly technical condition that V of W over V of Z should be bounded by log Z over log W to kappa for some kappa greater than 0. In our case, we'll only be really using kappa equals 1, but kappa equals 2 does come up in the proof of Linnik's theorem as well. This seems like an odd condition, but it's satisfied whenever G of P is equal to kappa over P plus theta of P to the minus 2. This basically tells us that we're tossing out kappa of the residue classes by P when we do this.
Can we quantify W? Who's W?
Sorry. This would be the product over W less than or equal to P less than Z.
This is true.
The W is less than or equal to Z, that's what we're missing.
Yeah, 2 is less than or equal to W is less than 0.
Okay. That's what I mean by quantifying.
Sorry. Yes. Okay. So we have this slightly technical condition, and we say then given some D, which is typically Z to some power, Z to some power S, where S is equal to log D over log Z. There exist what are called Sieve weights. So there's lambda D, upper and lower. We're going to use slightly funny notation, but upper and lower for upper bound and lower bound. Taking values 0 plus or minus 1. We should think of these really as the mu d's restricted to some subset of supported on only the divisors d dividing p of z, such that, so first of all, we have the sum over d dividing p of z, sum of d dividing n lambda d upper d of d needs to be bigger than or equal to the indicator of n b c d plus 1. And this is bigger than or equal to the lower bound version.
I don't think the G of D is present in this.
I'm sorry, you're right. Yes. In other words, this is formalizing the fact that we're doing inclusion and exclusion in a smart way to retain the upper bound and lower bound over there. And sorry, when you put the G of D's back in, you get some good estimates on, or you can compare them to the V and Z's, which is the quantity that we want to estimate from above or below. So less than or equal to G dividing P of Z. This is less than or equal to V of Z times some capital S of kappa of S. which looks like 1 plus big O of e to the minus s when s is really large, plus a small error term, and therefore I square the lower bounds.
Previously, over bounds involved in upper bounds.
I'm sorry?
So on the line above, lambda bar with the upper bar was an upper bound, and now it's become a lower bound.
Yes, so,
It's this thing that has an upper bound.
yes, this thing is bounded from above, and we can use this guy to bound, say, v of z, for example. Yes. And ultimately, our goal is to say, can I use this to bound that sum originally? And the answer is, well, yes. Right? This will provide both upper bounds and lower bounds for the sums that we want to say. There are these mysterious functions, capital F sub kappa and little f sub kappa. They're defined by a set of recursive delay differential equations. I will just draw a picture. So here's one. This is the s-axis, and the upper bound is really terrible when s is 0, but it kind of slopes down like this, more or less. And the lower bound, for any s less than 2, is stuck at 0. And then it sort of creeps up. And this 0 lower bound is a big problem, and it's a shadow of this thing called the parity problem that I would like to explain before we move on. So where these upper bounds and lower bounds come from is by being very, very careful and being very smart about how we run inclusion and exclusion over here. Which terms do we keep, which terms do we take? And ultimately, it does have to throw away some terms. It starts with a precise combinatorial equality, and then it says, well, some of these I cannot afford to keep because of the error terms that are eventually going to come back. And so it has to throw some things away. And that's where the inequality comes from. But there are cases where the things that we throw away are most of what we care about. So to explain this, we have these equalities or inequalities over here. Right? There is the indicator of n, p of z, that is, n is co-prime to p of z, has no prime factors less than z. This is equal to 1 minus the sum of p less than z of the indicators of p divides n. Right? So this says, well, if n does not divide p of z, then there must be some prime less than z that divides n. Yes, if n divides p of z, there must be some prime that divides n. So I start with 1 and I subtract that prime off. However, that might overcount numbers that have multiple prime factors less than z. So I have to toss in an indicator that says the lowest prime factor of n is equal to okay. This is called Bookstop's identity. And then we realize, oh, I can use this again, right? This says, this guy is the indicator of p and p of n, sorry, n and p of p is 1, right? N does not have any prime factors less than p. And I can reuse this identity and insert it in here. I get some kind of monster. Okay. But let's write down what that monster is. So this is 1 minus the sum p less than z, indicator, p divides n, times the sum. This time it's going to be p prime less than p of.
Mr. 1.
I'm sorry?
When we resubstitute, there's a 1.
Oh, yes, I'm sorry. Thank you. Yes. You get a 1 minus the sum. And this is our identity. Okay, great. When we expand this out and we distribute the negative sign, I get this is equal to 1 minus the sum over p less than z of the indicator p divides m, right, plus the sum over p prime less than p less than z of the indicator p and p prime both divide m, and the lowest prime factor of m is equal to p prime. Okay. And here we realize if I want a lower bound, for example, I can't afford to toss away some of these terms. I can't toss away any of these terms because the sign doesn't work in our favor. But if I want a lower bound, I can say this is bigger than or equal to 1 minus the sum plus the sum of p prime less than p less than z plus some additional conditions, which I'll call a2 of p prime and p. In fact, we can even make this precise by saying, well, I can keep track of which terms have I ignored and which terms have I kept, right? So this is plus the sum over p prime less than p less than z, not a2 p prime p, and so on and so forth. Right. So when we try to make an upper or make a lower bound, we're saying, forget these guys, right? I'm tossing away some terms in my inclusion exclusion. I get just a bigger than or equal to only these first two terms. So the problem is when you try to go back and sum over a sequence, right? Perhaps I should step back a little bit and say that this is for one n at a time. So I can multiply by any sequence of numbers an and then sum, right? So if I multiply this by an, I get the sum of p of z this one, an. And I get a lower bound that's bigger than or equal to the sum over all an, for instance, minus the sum of p dividing m an, plus the sum of over p and p prime of p prime divides m, and p prime is p prime. P prime is less than b. And what we've lost was the sum of an over these terms. And the big problem is that it's entirely possible for all of the ans to accumulate their mass on the terms that we've tossed out. For example, if an was supported only on primes that have two divisors, or sorry, not primes that have two divisors, only on integers that have exactly two prime divisors, right, we would expect to be throwing away quite a few terms. Yes, one or the other. And the specific examples are 1 plus or minus the Liouville function of that, right? These can be large or very small depending on the number of prime factors. And depending on this, we could be throwing away a lot of information here. And so this very loosely explains why we have a very poor lower bound here. This is very loosely called the parity problem, and it says that sieves have a very difficult time telling the difference between these two sums. Ultimately, we've only used very little information here, right? We've only used the g of these and the x's to relate this to our original sum after we broke it down. And so these 1 plus or minus n to n's look very similar to sieves, right? They have the same sort of distribution among the different residue classes. However, when you actually do the sieving, you end up tossing a lot of information depending on which sequence you're sieving. So, yes. Ultimately, when we apply this sieving technique to Linnik's theorem, we want to get off the ground, right? We want to get a lower bound that's better than 0. We want to say there's a positive number of primes in some interval, in some residue class. And that's very difficult to do if the best lower bound we can do is the trivial lower bound. There are two ways to go about this. Either we raise little s, right, a little bit above here, right, which means either being able to tolerate more error or sifting out fewer primes. And this means that our final result will not precisely be the primes in our progression. It may include some other muddier terms. The other choice is to be very careful and remember what are the terms that I've tried to toss away, and then try to reclaim some space there and say, no, I'm actually not tossing out very much. I can demonstrate that those terms are very small, and ultimately my lower bound will not lose out on too much. So that was our brief introduction on sieve theory. I think we have to move to another room, and then we will
Do your bodies down.
Are there bodies outside? Yeah, because you held that. Yeah. Right.
I can see some distribution.
Okay. So you go.
I think was it? I think I did. That's the well, it was a great. Whatever.
I unfortunately will be wanting to use the great black box again, but
I can write it on the other side while you do. If you want that.
that's our
It's
next
no
brief.
longer written on a black box.
Really black now.
So, so the black box again. This time, let's try to rephrase this using a sequence of numbers. Let an be a non-negative sequence such that g, a multiplicative function, satisfying some mild technical conditions on it, such that. So first of all, the sum of an over the multiples of any divisor d is equal to some capital S times g of d plus some r sub d for d dividing capital P of z and d is less than capital d. So this basically says that your sequence an has mass that's reasonably distributed in a consistent way that's predictable by this multiplicative function. So there's the signs. We need to say that the sum over d less than capital D of the absolute value of Rd is equal to little o of x times v of z, where again v of z is equal to the product of p less than z 1 minus 1 of p. Sorry, 1 minus g of p. This says that our errors are tolerable, right? And I can safely ignore them and keep my main term. Here, D is called the level of distribution. It says, well, this is exactly how much I can exploit this even distribution of my sequence. Then, you pick out these very nice subweights very carefully, and then you run inclusion-exclusion, and ultimately what you get out is that the sum over the integers n that are prime to p of z of a sub m, so this is our sifted sum, is on one hand less than or equal to x, the size of our sequence, times v of z, times capital X of kappa of log d of log z. It's little L of 1. And you also get a lower bound of something very similar, but with our lower bound subfunctions f sub kappa d log z. This is the great black box we'll be using. And remember that this little f is going to be 0 if kappa is 1. So in this case, kappa is 1, so I should write 1 here. In the case that we'll be using this theorem. This is only a good lower bound, because remember, we want to put a lower bound on the number of primes in an arithmetic progression. If log d over log z is strictly larger than 2. So we need to be able to do some work and do one of the amendments that we said. Right? Either save that term that we lost when we ran inclusion-exclusion and use the sieve, or somehow make capital D bigger or little z smaller in order to push up our log d over log z into a good range and get an actual lower bound. So we will be looking at the situation where we have a Siegel quote-unquote pole, where a quadratic character conspires closely with the Liouville function.
Siegel pole or Siegel zero?
Siegel pole, because that was the easier case. That was the case where we had a pole for ls chi. We could roll that out. Sorry, my notes got scrambled.
What is that? If we go back to, I mean, you started off telling the prime finite regression story, and we're trying to find the smallest prime finite regression story.
Yes.
If we're just very careful with exactly how it blows up as s goes to 1, etc., etc., do you get at least some quantitative information on the first one?
Yes.
It's just that Linnik does better, and that's why
Yes.
sustained in lights?
Yes.
Yeah, you get something exponential in Q if you use standard technology, and Linux is polynomial in Q.
Yes.
Which is amazing because normally to get polynomial about like that, you would need Riemann hypothesis, and it doesn't do that.
So, again, returning to Linnik's problem, we want to show that the sum of the primes that are congruent to A mod Q is strictly larger than 0 when we're looking at primes less than some polynomial bound in Q. This is Linnik's theorem. It says that if you can do this, then the first prime will appear in this arithmetic progression within polynomial.
And it's a capital L.
Yes.
Yes.
L for Linnik.
Yes.
And also Linux constant.
Yes.
The current S value is something like 5.
Yes, and it's 2 plus epsilon when there's a Siegel 0 present, which is kind of surprising. But because we're sifting a lot of primes out, I'm going to sift away the primes less than q to the L over 2. So, I mean, even if I get a bound on this guy, I'm happy. And so we should check that we can actually apply our black box. Does it have the right size? Does it have the right g of d? And are the r sub d's maintainable? So that's our first lemma. Our only lemma. So x is equal to q to the L divided by q, because we're summing q to the L things, and we're only keeping 1 over q of the numbers. And g of d is equal to 1 over d. And yes. So this sequence has a quote-unquote tolerable error. For z equals q to the capital L over 2, and d equals z to the 1 minus 1 over L, plus some epsilon, sorry, minus an epsilon. This should be z to the 2 times this, I'm sorry. So this says that we can run the black box if I take capital D to be this quantity, and I'm stuck with z down there. I should actually rewrite this in terms of q.
So what's the AN?
So the ANs will be the indicator of P congruent to A mod Q. So P lies in the residue coefficient. And D is equal to Q to the L times 1 minus 1 over L minus epsilon. And we can prove this pretty quickly because we just make sure that the R sub d's are small enough. So if we sum, first of all, the x and g of d, they check out. So
It's n is equal to a mod q, not p.
Yeah, A should be n equals A mod Q. Yeah,
I'm sorry. Yeah, so we can check this. What is the sum of p between q to the L over 2 and q to the L and quadrant A mod q. So there should be n, and we have d dividing n. Well, this is equal to q to the L minus 1 over, well, d. So we've got q to the L guys. We're only looking at one residue class mod q, so there's a minus 1. And then we additionally impose that n has to be a multiple of d. We're only keeping 1 over d, many of them, plus some r sub d. Right? And the r sub d's, well, what is the sum over d less than capital D, d defined over there, d divides p of z, again defined over there, of the absolute value of this term minus this term. We want this to be small compared to the main term that we want, right? We want this to be big O of x times b of z. So this is going to be the sum d less than capital D, d divides p of z, of, oh, it's going to be big O of 1.
That's our R of D.
Yes, because, I mean, this is only off by at most 1. And we can very, very crudely bound this by saying there's at most d many of these guys. So this is big O of capital D. This is a very crude bound, but it actually just works because x times v of z, again, running through the definitions and our claims, this is q to the L minus 1 times the product of p less than z, 1 minus 1 over p. And it turns out that this can be shown to save some log of d. So big O q to the L minus 1 times 1 over p. And this is good enough because the d saves an epsilon here, and that'll beat this big O bound. So that's that. The point is that we can actually use our great black box. But again, there's a problem because for this choice of z and this choice of d, right, if you do log d over log z, you're going to end up with something slightly less than 2. Right? This is like the square root of q to the L, and this is just smaller than q to the L. So this guy is just smaller than this guy squared. We're not good enough. Little f1 is still the trivial lower bound, and we want to do better. So what they do is they say, first of all, I need an assumption, and this assumption will be the presence of a quote-unquote Siegel pole that will let me kind of exploit some kind of distribution of the primes and or something.
So they is it Linnik or is it the newer the Matomäki?
Matomäki and Theorem.
Merikoski.
And Merikoski, yes. So they specifically said, suppose that the sum from q to the L over 2 less than p less than or equal to q to the L of 1 minus chi of p over p is sufficiently small depending on L. So, for some eta minus to be determined eventually. In practice, their eta minus was very, very complicated because they wanted to optimize the L that they got reasonably. And maybe an epsilon and wiggle room. So this is saying that 1 minus chi of p is 0 quite frequently, right? Which means that chi of p is frequently equal to 1, right? It was just like the case that Daniel described where L1 chi strongly resembled the Riemann zeta function and had a pole. But in claim, again, like I explained, this capital D is not quite good enough. I can't directly apply my black box. But if I give myself a little bit of room on the upper bound, I say, I don't really care about the terms only less than q to the L. I go to q to the L plus L over 2. So this sum applied to this sequence indicator and is equal to n mod q is strictly larger than 0. And this is what they claim. So the point of raising this upper bound is so that, oh, now my error is tolerable up to, instead of L, 3L over 2, or L plus L over 2. And if I keep the same z, then that will bump my log d over log z up to something around 3. And that's enough to get off the ground. The cost, however, is that the sifted sum is no longer going to only be primes, right? I'm not sifting all the way up to the square root of the upper bound. I'm only sifting up to the cube root of this. Right? So there will be some leftovers that are almost prime. They might have 2 or 3 prime factors, but somehow I need to deal with that. And that's what this guy here is for. It says, so long as chi of A is equal to minus 1. Yes. So as long as this is true, and as long as chi of A is precisely equal to minus 1, then we are expecting very few primes to satisfy chi, very few primes to be equal to A mod q, because then chi of q would also be minus 1. And this says that, well, there should be very few integers n that are also, chi of n is minus 1, that are a product of many such primes. And so the difference between the sifted sum, when we sift off the primes less than q to the L over 2, and the actual quantity that we're interested in is quite close. And we can actually, produce a good lower. So I do not want to erase the great black box. My writing is too big. Really, what we care about is this lower bound. So what did they do? They said we're going to do the sum over p less than q to the now L plus L over 2. So 3L over 2. So we're looking at how many primes here are congruent to A mod q. And this is precisely equal to, sorry, I'm missing that q to the L over 2. This is precisely equal to, well, I'm going to say q, so the n in this range, that do not have any prime divisors less than q to the L over 2. So n q L over 2 is 1. And this will be, again, indicator n is A mod q. Okay. So, like I said, these guys are not the primes, right? I have too many people here. And this will become a minus the sum q to the L over 2 less than or equal to p less than q to the L of so what they say is that, well, suppose you have some composite n that is congruent to A mod q, but is not prime, right? Then it must have a prime factor. So if n is here, but n is not prime, then it must have a prime factor such that chi of p is equal to minus 1. And that's what this condition is saying. I've taken off the prime factor of n, or one of the prime factors of n, that satisfy this. And then I say, okay, the n's that I got back were the n's less than q to the 3L over 2 with p dividing n, and n prime to q over 2. And I get the indicator with n congruent to A. And you might have realized, oh, you're double counting the guys with multiple prime factors that are -1. So, but I'm subtracting too many off, and that's in our favor. We get that we have this kind of inequality. To reiterate, I've sifted my sum in a way that I can apply a non-trivial lower bound, but that has induced some kind of error. Right? And the error is that there could be some almost primes lying around, and I'm trying to handle that error over here. And ultimately, I want to say that this guy dominates this guy. Morally speaking, it's because we don't expect very many things to be in here. Yeah.
Can you explain where you got the chi p's minus 1 condition?
Yes, because chi of A we assume to be -1. This is an important assumption. Right? So if chi of n,
So you took a Fourier function?
No.
Not quite. N is congruent to A mod Q, and chi of A equals chi of N, so chi of N must be minus 1. But chi is multiplicative, so if you do the prime factorization of N, then this is equal to chi of P1, okay, where these are the prime factors of N. If all of them are 1, you use multiplicativity and you get chi of N is 1. So at least one of them has to be minus 1. Yes. So again, that's why this condition is here. And this will manifest itself over here. So this one, we know we can handle using our lower bound sieve, and it'll give us a non-trivial lower bound. This will be bigger than or equal to, let's see, q to the 3l over 2 minus 1. So this will be the size of the sequence. This is kind of what we expect, times some product. So this is the product of a p less than q to the l over 2, and p not divided by q, and minus 1 over p. This is the v of z above, but we have to ignore the q's here. And then we get little f1. This is the lower bound. And if you compute log b over log z, so here z will be q to the l over 2, whereas d will be taken to be q to the 3l over 2 times, etc., etc. So it'll be slightly less than 3. And precisely it's 3l over 2 minus 1, and it's also 1 prime. Which again is approximately equal to 3 plus a little of 1. So this is our quote-unquote main term. This will be positive because, again, this guy is big enough. We can beat the trivial lower bound. And hopefully we have not subtracted off too many things here. This one I can again estimate using the sieve bound, using the great black box, because it's still a sifted sequence. Yes. However, I need to use the upper bound sieve, so this will be minus some sum q to the l over 2 less than or equal to p less than q to the l, and this time chi of p is equal to minus 1. And what I get instead is, well, because p divides n, n must be less than or equal to. So n less than or equal to q to the 3l over 2, and p divides n implies n is less than or equal to q to the 3l over 2 divided by p. Okay, so I can replace our little lemma here and say that capital D is equal to that thing in place of q to the l, and run the same argument. And the other thing is that this sifting level is still a little bit too high. Right? I might be sifting off too many things. If p is as large as L over 2, then this could get
Is there an inequality on n or an inequality on the number of some n's?
an inequality on n. So the condition
After the error.
n. This is still an inequality on n.
You mean
Why?
Sorry, n over p.
Okay.
So I can replace n with n over p and do some difficult rearrangements of the sum. And then I use the great black box, and I get q to the 3l over 2 minus 1 over p, because n over p is less than this thing, times the product of some primes less than some quantity, this thing, that I won't elaborate on, 1 minus 1 over 2 prime, times capital F1 through plus little L of 1. And that's all. So the reason I could put a capital F1 of 3 here is because sifting away all the primes less than q to the L over 2 is kind of a lot, and that might make F1 a little bit too big. But I can still be a little bit loose and say, I don't want to sift away all the primes. I only want to sift away the primes up to this thing to the 1/3 power. And ultimately, yeah, I'll be tossing away fewer n's here, and I can get a nicer bound like this.
Why does it still give you a lower?
Because you can lower q to the L over 2. That is a less restrictive assumption on n. So you're including more 1s in the sum, potentially. And yeah, the sum will be more negative. That makes sense. You'll be subtracting off more. But you apply the great black box, you get this quantity. And we see that a q to the 3l2 minus 1, q to the 3l2 3L over 2 minus 1 factors out. We can take away the great products over here. We can take away the big products over here, put them into the front. So this would be bigger than or equal to q to the 3L over 2 minus 1 times some great product times a little less 1 of everything that was in there minus the sum over these primes 2 to the L over 2 of 1 over p. But I can say, if chi of p is equal to minus 1, then this expression will be equal to 2. 1 minus chi of p will be equal to 2. And for the rest of the primes, chi of p will be equal to plus 1. And so this thing will be 0. And I can replace this with 1 minus chi of p over p and pick up a factor of 1/2 times capital F1 of 3 plus little o of 1. And this is a fixed quantity. This is some fixed quantity. But I have some assumption on how small this can be. And as long as this is sufficiently small, and this is where we take eta minus, as long as we make eta minus small enough, then I can make this entire thing positive. And ultimately the lower bound they get is bigger, q to the 3L over 2 over 5q. And this is strictly larger than 0. It could be very small, it's a somewhat tight lower bound, but ultimately this says, if you are in the situation where chi of p is frequently equal to plus 1, then I can do some clever sifting, and the error that I pick up when I try to apply a better lower bound from the black box is negligible. So that is one case of Linnik's theorem. Done. There is another case of when there is a Siegel 0, and ultimately it is sort of the same game. However, there are some technical details that make it much more difficult. For example, it is no longer a one-dimensional sieve. So kappa is no longer equal to 1, kappa becomes 2. And you have to work more carefully with how big 3L over 2 is. In fact, you need to push it up all the way up to 2L in order to have a good lower bound. So this wraps up the case where there is some conspiratorial behavior in chi of p, and I'll hand it off to Daniel to wrap up the case where there's no conspiracy.
Okay.